Welcome everyone to the 2024 Biophotonics Conference. Thank you all so much for joining us, and in this session you'll hear from Simon Bush, a product manager at Prior Scientific Instruments. Simon earned a master's degree researching plant cell biology and has spent a decade working in a variety of technical and commercial roles in the fields of microscopy. Today he'll discuss adaptive autofocus for microscopy. If you have any questions or comments, you can type them right into the conference chat box that is on your screen, and if you missed part of today's session, you can always come back later and watch it on demand. That's all from me. Simon, we appreciate you taking the time to present at the 4th Annual Biophotonics Conference.
Thank you very much, Jacob, for the kind introduction. Yeah, I'm very much looking forward to attending this conference and presenting Prior's autofocus solution. I hope to talk to you today a bit about how these types of devices work and how companies like Prior are trying to improve the technology to work with new types of sample, such as things like microfluidics that we see coming onto the market increasingly in research and in the industry as well. So just to start off then, what is an autofocus, or what can it do for you? So kind of as the name suggests, it recaptures or maintains focus automatically without the intervention of a microscopist or other user. But maybe in contrast to contrast-based autofocus, which microscopists may be more familiar with, a hardware autofocus actually uses light rather than the sample image itself to determine where focus is. It does that by collecting a reflection from the sample. That means either directly from its surface or some other plane within the sample that has a refractive index change boundary in it. And then it adjusts the focusing system of the microscope via a control loop to always maintain focus or bring the sample back into focus. To give you an idea of what this means, I'm going to show you a video in the next slide, but just what you can see on screen on the right hand side there is Prior's flagship autofocus solution, the PureFocus 850. So I move over to the next slide. So in this next few seconds, you'll see a variety of different samples which have all been arrayed together under a microscope objective. And what we're doing is we're using one of Prior's motorized stages to scan around the sample. And you can see here that we've got all sorts of different materials. We've got resin, we've got metals, we've got plastics that all will reflect and interact with the light coming from the autofocus in different ways. And what you can see, if I just go back one slide and play the video again, is that regardless of what material we're focusing on, regardless of its structure, the autofocus maintains a good level of focus on the sample. We're dealing with different levels of reflectance, and we're able to adapt to things like that. And I'm going to explain through the course of this presentation how that works. And the things that Prior's system can do that maybe others can't as well. So there we are. What is it used for? What's a hardware autofocus used for in microscopy? Well, we see increasingly that there are a diverse array of applications that the autofocus is used with. Typically, maybe those of you from the life science background will be familiar with it for life science microscopy due to time lapse. So you're maintaining focus on cells over a 24-hour, 48-hour period, looking for changes in morphology, changes in expression of different proteins and other things like that. And that's where many of the commercial solutions that have been around for a while have come from. But equally, things like medical devices and microfluidics, as I've said, we see increasingly coming onto the market. We're seeing more and more requirements that autofocus be used for those sorts of applications for time-lapse, because by their very nature, you're looking at something that is dynamic and you're wanting to look at things with temporal resolution. Then again, as we saw in the video, industrial inspection. So this can be in a microscopy lab, or you can have an optical system set up above an inline processing routine as well. And finally, in the semiconductor world, where you've got very, very large samples that you want to scan over, but you don't want to take too many images, you don't want to have to be doing an autofocus routine, taking multiple images in the Z-axis at any given time. either. And again, we're seeing this type of technology increasingly applied into the microfluidic space and the life science space as well. What are its advantages then? Well, the key advantage of a hardware-based autofocus is that it provides you with the ability to very, very quickly capture focus. In contrast to contrast-based autofocus, where you have to take multiple images to determine where focus is, a hardware autofocus doesn't require that. We've seen instances from our own experience where we've been able to reduce scanning times of large samples by up to 95% compared to traditional methods. Hardware autofocus is also sample agnostic. So if you think about a fluorescence expression in a live cell, for instance, that could be quite sparse and diffuse. Or if you think about some of the components that make up a semiconductor wafer, they may also be very, very low in contrast. So those traditional methods don't work so well. Hardware autofocus simply looks for a reflection, and as a result of that, you can maintain focus on things that may be quite difficult to find the focal plane of, either by eye or with one of these contrast-based methods. As a result of taking fewer images, you'll ultimately result in lower data volumes for your experiments as well, which is something that we're finding is increasingly important to our customers. They want to make sure that the data they have on file is useful and is as small as possible, so they can avoid needing to invest in data storage hardware. It can decrease experiment time, as I said, scanning large samples. The less images that you have to take, the less refocusing you have to do, the faster you can get through things. And as we know, throughput is really, really important in the microscopy field. It's resistant to environmental factors as well. Think the traditional use of this sort of technology for time-lapse is to account for thermal changes around the microscope that might induce a focus change as well. And also because the types of light source that can be used with laser autofocus can be quite weak as well, you can maintain your cells in the microscopy environment that much more easily. So how does it work? How do we get this light coming down onto the sample and then detecting it and then determining where focus is? That might not seem immediately obvious without, as I've said, requiring an image of the sample. So at a basic level, a hardware autofocus contains a diode, either an LED or a laser, and that emits light down onto the sample that's reflected into the light path via a mirror or dichroic, and that's what's represented by this diagram here. That signal then needs to be collected and detected. So what the autofocus then has to do is contain a sensor that light can be then refocused back onto. That's represented by the blue signal here. So for those of you familiar with industrial microscopy, this is very, very similar to, I would say, reflected bright field imaging, for example. If we then move the sample out of focus, you can see that we get a defocus signal on the sample and we get a defocus signal on the sensor. And if we move the sample back up as well, we end up with the same effect, and just the sample is focused below the sample and below the sensor, as opposed to above as per the previous slide. I should say as well that none of this really interferes with the actual imaging process. The light used for imaging the sample is passed through the dichroic and goes off to be collected by a classical microscopy camera in many cases. So whilst in the previous slides you could see how we could differentiate between being in focus and not in focus, what we can't do without making a further change is to determine which direction we need to move the sample to reacquire focus. The way that these devices do that is you simply fill half of the back aperture of the objective rather than the whole back aperture, and that allows you to collect the reflected light up through the other half of the back aperture. The net result of this is that the light is still focused on the sensor when the sample is in focus, but this, as you'll see in the next couple of slides, is what gives us directionality. So then if we go through the same animation, but with the split signal, we can see that the signal, whilst it's defocused at the sample level and is then reflected back up through the objective, when it comes to being focused on the sample, the signal is still focused above the sensor. It is now only defocused onto the sensor on one side, onto side B, as you can see here. If we then follow the example through, we can see as well that if we move the sample up and we are focusing our incident light below the sample, the collected light ends up on the other side of the sensor. And that's how we form the basis for a feedback loop to control the focus position. How is signal detected then? The Prior's Pure Focus uses a line sensor. Other models available on the market use a split sensor, and all of these devices are doing really is collecting the number of photon counts on each side of a sensor. So where the sample is defocused below the sample, where the sample is too close to the objective, the signal appears on the A side of the sensor. Where we are focused above the sample, we can see it on the B side of the sensor, and simply that produces the ability to do a calculation that produces an error signal value. And we use the sign of that error value, either +1 or -1, to determine which direction the feedback loop needs to close in order to bring the error to 0. The advantage of a line sensor as opposed to a split sensor is that you can still determine the intensity of the signal when the sample is in focus. In a split sensor, you've got a dead zone between your A and B sides, and in a line sensor, you have that continuous array of pixels. What Prior's Pure Focus does is it allows us to make interpretations based on the intensity and morphology of this signal, even when we are in focus, to introduce certain safety features that I'll come on to later. The basic principle then of the system is, as I've said before, a light is emitted onto the sample, it's reflected back onto a sensor, it is transferred to a controller of sorts that then sends a signal to a focus actuator that then induces a movement in the sample to bring it back into focus. Okay. In this next section, we'll talk about how focus position is determined and give you a feel for how we can deal with different sample types. So the Prior's Pure Focus contains an offset mechanic, and what this allows us to do is to correct for differences between the par focality of the sensor in the Pure Focus and the camera in the imaging system. So you can see in this scenario, the light is theoretically focused onto the camera. That's the box at the top, but it's not focused on the Pure Focus sensor. By moving a lens in the Pure Focus itself, we can adjust the par focality of the system to bring the light emitted by the Pure Focus into focus on its sensor. This has an additional benefit in life science imaging, where we can adjust for the difference in position of the reflective plane in a life science sample, the cover slip, and the sample itself, your cells, which are non-reflective. So if we consider the red signal to be the signal from the Pure Focus and the yellow signal to be the signal that you're using to image the sample, you want them to be almost focused at different planes because they're going to be used by different sensors to do different things. If I focus on the sample, I end up defocusing the signal on the sensor, and the Pure Focus will try to recapture focus on the top of the cover slip instead. By using this offset mechanic, by moving that lens, we can split these signals focal planes apart and thus maintain focus on the sample you want to image whilst tracking the top surface of the cover slip. The pure focus also allows you to have multiple offsets, which can be really useful in microfluidic systems, where you may have cells adhered to the cover slip bottom or other parts of the channel. Again, just by adjusting that offset value, which can be done dynamically whilst the autofocus is active, you can actually image multiple focal planes of interest without having to do a complete Z-stack image of the full thickness of the well, again, reducing those data volumes, as I mentioned before. Next is just a video of how we acquire an offset. So this movable lens is motorized, and what the system does is it goes through a loop of trying to find an offset value where the signal error detected is 0, and that means that from a user's perspective, it becomes a one-click operation to determine where the correct offset position is, as opposed to having to do lots of manual adjustment on the microscope frame. The next kind of interesting topic about focus acquisition and determining where focus is how do we process the signal? How do we account for variation in the sample surface? So if you think of something like a semiconductor wafer, it's likely to have different components on it that may be at subtly different heights. For this reason, Prior's Pure Focus has two modes. You can see both of these in the video. So this video here is of our spot mode system. So what this system does is it looks for a specific point within the field of view and trying to maintain focus on that. But because of the different focus heights that we see in the sample like this, you can see that the focus is jumping up and down ever so slightly, and different features come in and out of focus as a result. Now, obviously, that would be a problem. You're not acquiring a good image, and thus you might resort to doing volumetric imaging. But what we've developed to go alongside that mode of operation is something called line mode. Line mode takes a weighted average across a bigger area of the field of view. And as you can see, just over the same area of the sample, we get much more consistent focus. We're able to see all features in focus at the same time as well. So you can see how by processing the sample in a different way, processing the signal in a different way, you can achieve a better focus result. Yeah, that's right. So just to kind of give you an overview of which mode is better for different applications, for flat planes and tilted planes such as cover slips and well plate bottoms, or even undulating surfaces as we see in some types of sample. Slice mode tends to be better, spot mode tends to be better. This is because we're able to deal with the tilt in the plane better in that mode, whereas samples that have surface variation in reflectance or in their actual surface height, or where they have very, very weak reflectance, line mode tends to operate better because of that averaging, and also because the intensity of the signal in line mode that the signal detects tends to be much higher. And we can kind of see that represented in these next two animations. So as we scan around focus, this is broadly what the signal does on the sensor in both cases. But where the sample introduces tilt, where the sample is tilted and maybe is deflecting the signal in a bit of an interesting way, while spot mode is more resistant because it keeps more of the signal on the sensor, whereas in line mode, because the signal is more tightly focused onto the sensor, there's a chance it may fall off. Next, we'll talk about the light path and some of the considerations for some of the home builders in the audience about how they might integrate a device like this. So there have been two real different ways of mounting an autofocus system on a commercial microscope frame. One is to mount the autofocus on the camera mount, where you may split off, you may introduce a beam splitter in front of the camera or have a dual camera port and mount the autofocus on there. The main challenge with mounting the autofocus like that, however, is that the signal emitted by the autofocus must pass through all other optics between it and the sample. And you also need to have more knowledge of the optical system you're integrating with to ensure that the signal returned by the objective can actually be focused onto the autofocus sensor correctly. Prior's field focus, on the other hand, is mounted in the infinity space of the microscope. The illumination that you use must therefore pass through the autofocus, which may cause its own set of problems, but I'll talk about those in a minute. But what this does give you, it gives you the ability to position the autofocus flexibly in the light path. That means you can position it behind the objective, or you can position it in some other location that suits your optical design. Just to kind of explain a little bit more about how the optical elements may interfere with the operation of the autofocus. So if you have a fluorescence light source, in this case represented by the green arrow, that's going to be reflected down onto the sample, and the dichroic used to do that will block other wavelengths, such as the wavelength being emitted by the autofocus. But with the autofocus being mounted in the infinity space, you simply need to change its position, and then you can get the signal emitted by your fluorescence light source and the signal emitted by your hardware autofocus down onto the sample, and thus they don't interfere with one another. The PureFocus 850 transmits all visible wavelengths, and our PureFocus 690, which uses a 690 nanometer diode, which will be released quite soon, transmits a lot of the key wavelengths for Raman specifically. Now, the main operating requirement for a hardware autofocus comes down to signal to noise. So we want to make sure that we detect as much as of the signal emitted by the hardware autofocus as possible, while excluding all other signals from the sensor. So things like turf, for instance, can introduce additional peaks onto the PureFocus sensor. Back reflections from certain objectives can also introduce additional signals, and transmitted light as well, where it's very, very intense, can also be reflected by the dichroic in the hardware autofocus and introduce an additional signal. We can suppress this optically by using a cleanup filter, but we can also do this mathematically by simply doing a subtraction of the signals that we see on the sensor itself. So it's a really nice way of excluding things like low-level white light that's coming onto the sensor. The other way we can deal with this is by adjusting the activity of certain pixels on our sensor. So in this scenario, maybe there's a turf signal that's appearing on the sensor in the PureFocus. We can turn off a certain subset of those pixels to exclude that from the error signal calculation. We may also see multiple reflections from the sample. So this little video here is a representation of the reflections that you might see from the top and bottom of a cover slip and the top of a slide. But within the autofocus, we have the capability to deal with this. The graph on the left-hand side there is a representation of the two signals that you might see from the top and bottom of a cover slip. So the first signal over here is from the top, and then this diffuse signal here will appear as a peak when that is brought into focus, like so. We use an interface correction method that allows you to reposition the objective in advance of actually performing the closed loop operation, to ensure that you always home in on the correct interface within the sample. So we've just got a little video here to represent that. So what we're looking at here is just a completely defocused sample, and you can see as I've turned the contrast up that there's a sample waiting to be imaged. But in turning the servo on, we've identified one of these other interfaces which we don't want to image. Moving back to our plane that we were at previously, we've now turned this interface correction on. And now what you'll see in just one moment is the correction activating and bringing the sample back into the correct plane of focus. We've used our correction capability to avoid locking in on the wrong interface. Finally, let's talk about some of the performance characteristics of our pure focus as well. So here we have just a representation of how the system can recapture focus from long range. So we're about 10 millimeters away from focus. We're at the point of activating the servo, and you can see both the image being acquired in focus and the autofocus actually operating as well, bringing the objective down towards the sample on this microscope. Focus tracking. So if you think about a semiconductor wafer, it's very large, at high magnifications, your depth of focus is very small, and thus it can be difficult to maintain focus on the sample as you move around. If we just move on to the beginning, now with the servo activated, we can move across the majority of the diameter of this 4-inch wafer once it begins without losing focus at all. There we are. So you can see the difference that an autofocus can make there. It can make operating a microscope that much more easy when using these very large samples at high magnification. System protection. So modern microscopes today are routinely equipped with software limits and hardware limits, all of which can protect the key components of the microscope. But with the laser autofocus system and using different types of sample, there's always the risk that those preset limits aren't adequate to protect both these samples and the objective. We have the ability to help with that within the pure focus. What you've just witnessed there is what will happen if the system is not set up correctly and sufficient protections are in place. There's the potential for the objective to crash into the sample while hunting for it. If we go through this next example, our what we call servo limit function allows us to set a fixed range from the point of activating the autofocus through which the objective can move, and outside of that range, this servo will temporarily deactivate. This can help when moving between adjacent samples as well. So if you don't have a protection like this, you can drop into a void between two adjacent samples and thus not be able to recover your focus position when you try to image the second one. Whereas if you've got your servo limit function turned on, you can stop the objective dropping into the void between the two objects and thus recapture focus on the second one once the objective approaches it. Now, right back at the beginning of the presentation, I mentioned that the pure focus uses a line sensor, and that allows us to look at the signal that's reflected by the sample even when it's in focus. The way we can use that is we can effectively look at whether we are detecting a sample or not based on the reflection that we see. And this can help in those high throughput scenarios where you're introducing samples under the microscope and replacing them with other ones. So under normal operation, you'll focus on the sample and achieve focus. But if we take away the sample, the objective will just hunt for it and not be able to find anything, and thus run into the hard limits of the microscope. If we were then simply look at the total amount of signal collected by the pure focus, when we're imaging, we can turn on this function that we call inhibit. Then if the signal isn't above or below a certain threshold, nothing will happen even when you activate the servo. And this can also help with samples that have variable reflectance as well. So if we're in a less reflective area of the sample and we turn the servo on, we'll achieve focus. Then if we scan over to a more reflective area of the sample, which produces more signal and that's detected by the pure focus, the sample may become oversaturated, the focus recovery may not be happening in the correct way. This sample protection inhibit function prevents these unwanted focus movements that could be less controlled. Finally, probably one of my favorite features on the PureFocus is our ability to adjust the power of the laser that we put onto the sample dynamically. And I'll just walk you through these 3 examples. So the way this feature operates is that we have a target amount of signal that we are looking to detect from the sample within a certain range. And if the amount of signal falls outside of that range, we want to increase or decrease the laser power appropriately as to not oversaturate or lose all the signal that we need for autofocusing. So in this instance, material A provides us with the correct amount of signal. If we move over to this different area made up of material B, we start to detect too much signal. It's oversaturating the sensor. The PureFocus can respond to decrease the laser power and thus achieve a good signal to noise level to determine focus. And finally, we can move over to material C, where the reverse is true. We've moved from a highly reflective area to an area that's less reflective, and we can go through the reverse operation. We've not detected enough signal. There isn't enough signal to noise to determine where focus is, so the laser power can be increased on the fly dynamically in real time to enable you to recover the performance of the autofocus. And we can get a little nice representation in this video of how this happens. So we're first going to look at moving to an area of the sample that is maybe weakly reflective. We're getting poor performance of the autofocus. As you can see, the focal plane is oscillating. Now, if we turn the correction on, we can move over to the same area of the sample. Just one moment. So just as I was saying there, the autofocus dynamic laser power adjustment enables us to make sure we have sufficient signal to noise to maintain appropriate focus on the sample. That is the end of my presentation. Thank you very much. I look forward to any questions.
Thank you, Simon, for joining us to discuss time-lapse microscopy. To everyone joining us in the audience, if you haven't already, you can type your questions and comments into the conference chat box, and do not worry, if you have not been answered yet, you will be reached via email at a later date. This session was presented by Prior Scientific Instruments and hosted by us at Photonics Media. We certainly hope you're enjoying the 4th annual Biophotonics Conference. Thank you all so much for joining us.